Welcome back. We're in the middle of our unit on universal programming. You might want to watch the video on that before watching this one. The basic idea is there's a style of programs that we can design which anticipate the need for changes. The program itself isn't universal as it'll always run forever, but it anticipates how to adapt and use the best ideas of future programs. It's an interchangeable, pluggable architecture. This is the key thing that the mathematics can bring to it. So now let's take on a story problem that uses a universal design. I'm talking about a low power device, something like an audio player or any kind of sensor that might run off a battery. When the power mode is high, the device can load all the files into memory to be ready to play at a moment's notice. That's a convenience the user might want, or the best functionality for your device. But many systems will also have to have a low power mode where they turn off and remove from memory some of the things that aren't necessarily being used. This lower power mode will be slower at some of the activities because that information is no longer available ready to go. But it allows the machine to no longer power that part of memory and therefore stores a little bit more battery life. These two behaviors are not the same, but they have to interchange. They have to be switchable. This is a situation we'd like to think of as a universal plan. We'd like to design a data type that could talk about compression and decompression without having to switch in every single program. We don't want every program to have to worry about the low and high power modes. We'd like to design single data types that, when told, can switch between the two behaviors. So let's see what we could do to articulate this type of need. What we'll be using is a single universal property, but we'll start without the universal property and see what challenges it brings up before we solve it using a universal property. So here we have it. I have two miniature programs that could try to emulate what we're seeing in this high power and low power mode problem. But in fact, I'm going to try to think about this as relating to any task. So I've isolated my task as a function from some inputs to some outputs. In our story problem, this means to take an audio file and convert it into memory storage, decompress it. Now that task could use memory up, and we may not want to always use that because it could affect our power. So we have two modes of evaluation. In the eager, this will be the most convenient, get the data into memory so the user can use it quickly. How does it work? In this model, I have one formation rule. I create the data type called eager. It depends on one parameter, the function, the task that we're going to do. We could swap in new task and we would get an eager evaluation for that new task. That's what makes this a very good long-term program. It doesn't depend on decompression. It could depend on many other tasks. Inside my program, I store some internal data called myB. We'll see what it does. My constructor or introduction rule takes in the task to be done. This could be a file name that we want to decompress. In this model, because it's eager, we're assuming the full power mode, for example, we should go ahead and do the task right away and store the result internally. That way, when a user finally gets to wanting that data, they simply call it up and it's available right away, ready to use. That's exactly the model we're thinking of here. As soon as we see that there's a file we could play, we put it into memory, it's easy to spin up. What about the low power mode? The lazy mode is what's modeled over here, and it looks almost the same. You see that the file name is now called lazy instead of eager, but the structure of the formation is the same. It still depends only on our tasks F from A to B, and that's a pluggable task. One task could become a different task. So far the formation rules are just simply named differently, but they're the same data type so far. The constructors are also the same. Instead of calling it make eager, I've called it make lazy, but it takes in an A. And from the outside, that's all I could see. Two formation rules that look the same, two introduction rules that look the same, and if I scan ahead, I see the elimination rules are the same. They're finally also going to have identical computation rules. Because remember, the computation rule isn't about telling you what to put in the program. It's trying to tell you how does the introduction relate to the elimination rule. And we see that in this model, what I do is I take my data A and I store it temporarily. I delay evaluation. I don't know if I want to read that file yet because I don't know if the user will select it. Once the user actually calls the file, then I'll go ahead and apply the decompression. I've delayed the work. This is the better model for the low power mode. Notice these are identical data types. From the perspective of the types, all I see are the formations. That's the part that leads at the top to tell me how to create the data type. The introduction rules, how to put data into the data type, and the elimination rules. Because these are all the same and have the same computational rule, I could say these are equivalent data types. Now the question is, which one do we want to use? The answer is both. We can imagine a scenario where our device switches between these. It starts out in high power mode, goes to low power mode, and needs to turn the eagers into lazies. Once it has the lazies, maybe I plug it in, and now it should switch back to eager. Why don't we draw what that would look like? We'll see in a minute that this is where a universal design would have done better than what we've done so far. So let's run through the data type using these pictures, these commutative diagrams that we know can help us model our introduction, elimination, formation, and computation rules. Our formation rule starts with the data f from a to b. That function is the task that we're going to apply. Now, picking these two data types, we saw that they were identical in structure, so it shouldn't matter which one I put first. So I've simply put lazy. I have a task that introduces something lazy. That was our make command, make the lazy program. Once we created that, I now have data of type lazy, lazy of f. Once I take that lazy, I can get back the values of b. That was the as b command, which simply applied the function to the stored data a. The result would be the same as having applied the function at any point in time. We simply delayed when we would do it, and then we actually did it. That saved us on power. Now, when we compare this to the eager, it has the same overall structure. It starts from a and creates the eager value, and then when asked, it'll return the value b. In this case, it's the opposite point in time. The eager evaluation has done the work already and it's stored it inside. What is the universal property that we would like? We want to be able to interchange them. We would like to go from eager into lazy. And here we find the flaw. We have no idea what task F is. Maybe it's not even reversible. Maybe once you apply the task, you're done. You can't undo it. If eager has already done the task, then how could we convert it back to the lazy one that doesn't have it? We simply have no tool to do that. There's no natural way to take the data type we have here and, having already applied F, somehow recover something that wouldn't have applied F. We've already done the work. This is failing to have the arrow we need. A universal diagram has to take a piece that will become the parts of the formation, add introduction or elimination rules in such a way that anybody else with the same introduction and elimination rules will be able to transfer their data into ours or ours into theirs. In this case, we cannot do that. We cannot call lazy and eager universal constructions for this problem. But is there a way we could have? Well, the short-term solution is simply to add more things to our data type E. Our eager evaluation could have stored the input value A as well as the value B, and then it would have added a function called as A. Once we have this, when we need to create the lazy from the eager, the lazy one could call the as A and recover that piece of data. But this is no longer switchable, it's no longer pluggable. This data type is no longer the same list of instructions of introduction elimination as this one. We've definitely changed the behavior. There'll be one set of programs that work with eager, and they won't all work with lazy. So we need to do the same thing to lazy. We need to update the lazy type as well. And so we'll add a new command called def as a to match this one here. Notice in the lazy program, it's a definitely different program. We're not storing two values because the lazy didn't actually pre-compute the myb. This is the key thing about universal programs. We don't actually write one single program. What we do is we write one single interface to talk to the program. And this way we can change the behavior underneath the covers and swap them in between each other using a reasoned logical progression. Let's match the pictures. I've now added the tail back. Our as a function has to come out of our data type back to A, just like we have over here. Def as B and def as A, def as B and def as A, two arrows coming out. It's an extra elimination rule, and it applies to anything that's trying to match the same problem. So we have one out of lazy, and we'll also have one out of eager. Now we can ask, is there a way to turn eager into lazy? And we see that there is. We could, starting with our eager, use the as a command to create the piece we need, then use the make command on lazy to get the map we want there. We could fill that in with a solid value now. Now let's stand back and see if we can improve our description. We just discovered that the line from eager into lazy was defined by going through as a and back up. But we realized this could have been done redundantly. We have two arrows going into lazy. One is the make command and one is this new universal command. We probably could get away with just one of these arrows. In fact, the down arrow should do. So here we have our new commutative diagrams. These will be the ones that are truly universal, and we'll update our code to match. Remember, a commutative diagram is hiding an equation in disguise, so I've started to write the equations to go with it. We start with the task that we want to wrap in two different ways, either lazy or eager, low power, high power mode. Our task then gets wrapped by these two commands. We've now seen that the downward arrows are all we need to be concerned with at this stage. How do we get the information out of whatever we packaged? I'm calling this one lazy, but it could have been eager or any other intermediate type as well. What it does is if there's ever data of that type, then I can get out of it something from A or out of it something from B. But the rule of the commutative diagram is that if I go this path, it should be the same as that path. Set in symbols, f of L as A is equal to L as B. This is the kind of behavior we want. It's an interface that everyone can agree to. It's a commutative diagram. It's an equation. Now we compete. We take another data type, such as eager. This could be the decompression I'm storing in memory. Here, if I have an instance of E, when I apply F to E as an A, it should be the same as getting E as a B. And we see that these two maps have to therefore send this data the same way that data has. So now we have two competing challengers. We have the eager and lazy. If one of them is universal, then it should be able to take in the behavior of the other. In this case, let's imagine that lazy is universal. It can do everything that eager could. The key thing we saw was that this would allow us to interchange between the two. So we need a way to create something lazy from something eager. We need this downward arrow. Notice this has to still be a commutative diagram. So if I start with eager and I ask for the A part of eager, that should be the same as first creating a lazy version and then asking for the A part of the lazy version. That tells us how to program it. Same thing with the eager on this side. If I take the eager and ask for the B application, that should be the same as first creating the lazy version and then asking for its B application. In both scenarios, I'm able to use eager and lazy in somewhat similar ways. In fact, it could even go backwards. If eager is universal, then I could get an arrow from lazy back to eager. I could now switch between the low and high power modes, confident that I will never have to reprogram that interface. Let's see if we can make a matching implementation done. So let's stand back and review how we've gotten here. We started with a task that we wanted to evaluate or possibly not. We had two modes in mind. But have we really achieved a universal, or have we simply designed for eager and lazy? Let's put this to the test. The key thing about eager and lazy was that sometimes on the eager side, we wanted to get closer to the B, have a value that's pretty much what we already want as a result. But on the lazy side, we wanted something closer to A. You can imagine a new scenario in which you want to store based on size. You can imagine a large data file, maybe you won't decompress, but a medium-sized file you would decompress. You have many options. This is what universal programs allow us to do. So if we design correctly, we'll get rid of lazy and eager in the back of our minds and just design based on the diagram. We saw the key thing was to put forth the elimination rules, that from our data set, we wanted to be able to get something into B. And then we also saw we would need to get something into A if we wanted to later introduce it. So let's put those pictures together. I want a universal type, which lies somewhere between A and B. You can get to B from U, and you can get to A from U. From here, I need to add the universal property, which is that if somebody comes along to challenge it in these same eliminations, I can match them. And there we have it. We now have that from the challenger, we should be able to introduce data of our type U. Ours is universal, even if theirs isn't. To form my data type, I have to have a context in which I have a function from A to B. That entails all the properties we need. A and B have to be data types, and there's some version of a function already. Once I get that, I see that I'm introducing a data type that I'm denoting as UF. So it'll be U bracket F in this notation. Remember, when you go to specific programming languages, you'll have lots of idioms to choose from. For example, we were illustrating with class and then a name. What we'll be using is the sequent calculus. It's one of the oldest notations, and it's universal for programming. Once you write it with sequence and you know how to read sequence, you can put this into almost any programming language. After we've got our formation rule, we now need to get data of that type. We need introduction rules. Introductions come from data that goes into our data type, so we should look at our picture and find which arrows go into UF. And it's right here. We see that the result depends on C, J, and K, all the data we see here, and it comes into our UF, so it has type U:, UF. What does it need as its premises? All the data we see. Given that part of the information, the challenger and its two functions j and k, we can introduce data of the kind we want. Now, how do we use it? What are the elimination rules? Elimination rules are the ways to get information out of the data type we've created, so they should be the arrows that come out. We see already that this picture already has arrows coming out, so those will be our elimination rules. We see that in this picture, the eliminations only depended on this top part, and therefore they just need one piece of data of our new data type UF, and from that we will be able to eliminate to get something of type A, that arrow, or something of type B, this arrow. Of course, all of this takes place inside of a context, which I've made it explicit in this language now. This all leaves us to the final C. The C is the computation rule, or sometimes called the comprehension rule. These are commutative diagrams. Any two paths to the same place should be equal, so there's an equation we need to write down. We can see right here that if I start with C and come down through iota, then through pi, it should be the same as having gone through j. Let's write that equation down. That's our first computation rule. I see that the two conclusions are the two commutative diagrams, this one and that one. How do I get the premises? The premises are basically to take what we do in our introduction, those qualities, and add them to whatever's needed in the elimination rules and compose them. Those should be equal. I now see that if I had these data in my context, I could create the iota version. And once I have a iota version, I could use this elimination rule to apply pi a, and it should come back as j. Notice this is telling us how to program it. If we want the eager version, we could pre-compute this value as simply j of c, and then we'd be fine to return that. In the lazy version, we might store c and j and k and wait till we're asked to use pi of a to then compute the j at that time. In an intermediate version, you'll have different logic in between. The same idea happens over here. Now there's one last catch. Notice there's a further commutative diagram right here. There's a missing equation or story. So if we add in that we also have to have that f of pi of a of x equal pi b of x, we have all the features we need. This is now a universal program. This is something we could give to any future designer, and they could interchange it with a lazy, eager, or some intermediate application. They might even find new applications having nothing to do with eager and lazy evaluation. This is now a universal program that lets us switch how we want to evaluate our function f based on the needs of our individual tasks. If you learn this type of programming, you'll be able to build interfaces quickly that behave well even into the future because they have a mathematical reason. They're built out of equations, and these equations, once solved, never need a new solution. Until next time. That's how you take care of your chalkboard.